The next talk is going to be given by Nikul. I don't have his last name, I'm sorry. Nikul is a fourth-year PhD student at University of Maryland College Park. His research interests include ultra-low power sensing, wireless communication, and embedded AI. And this talk is entitled ThermWare Towards Side-Channel Defense for Tiny IoT Devices.
Yep, there you go. Thank you for the introduction, Neil. Hi, everyone. My name is Nakul Garg, and today I'm going to present our work on ThermWare, which is on side-channel defense for tiny IoT devices. And this is a joint work with Erin, Irtaza, Jenny, Professor Jun Han, and my advisor Nirupam Roy. And we are from University of Maryland College Park. So as we all know, the world is becoming more and more connected day by day. And the IoT devices are leading this charge. In fact, there are 20 billion IoT devices, and within just next 2 years, they are expected to double to 40 billion. With one clear trend in these increase is that these devices are becoming more and more compact. And they are becoming even more complex and application specific. However, one problem with miniaturization is that it brings in new vulnerabilities to security and privacy attacks. These devices have access to our private spaces and private conversations with maybe always-on microphones which are listening to us, and we never know that if someone just installs a malware and listens to our private conversations. And there has been already a lot of security work done in the past, right? However, we still see that these attacks are not new. There has been already like spying on public cameras which are connected to internet. People have actually had pacemakers which patients are using and try to alter their heart rate just by installing a malware. And it's a matter of time that these kind of attacks will now be even more application specific for tiny IoT devices which are so resource constrained. And while like security research has been there for 30 years, I would say that this is a very niche specific problem that we are trying to solve for these resource constrained environments. And these pose like a new security threat because these devices are often space limited and they try to avoid as much debugging ports as possible. So you cannot wire an Ethernet or a USB port and see what firmware is currently running. They have limited compute power, and often they have very specific architecture for that application, and they lack like a general operating system for which you can install an antivirus or something like that. Our solution is made on something a bit unintuitive. You have probably heard of side channel attacks, right? Well, we are building something for side channel defense. A side channel exploits some extra information which is generated from a system's implementation. This could be some random sound which is generated while the processor is computing something. It could be the power consumption traces that leave a trace on what operation was running instantaneously, or the change in the clock skew of the oscillator. And sometimes, due to the oscillation of current in the PCB traces, there are electromagnetic rays which are emitted, and someone can just hack into it and see what's running into it. In this work, we are taking advantage of these side channels to develop a new security approach. We are introducing a defense system that leverages thermal side channel to detect malware on resource-constrained IoT devices. The thermal side channel allows us to non-invasively monitor an embedded system and detect if a malware is running on these devices. So let's take a deeper dive into this. We have a high-level code that a developer wrote, right? And for a microcontroller, these high-level code is just converted into a set of instructions which are assembly-level code. And these are limited instructions which are very simple, like moving a register to another, adding and subtraction operations. if we look at the hardware level, all these instructions do is just switch on and off some transistors and put set some memory in the register values, right? And it inevitably generates heats because of the electricity. So if we could tap into these heat signatures and see that what area of the board is getting heated up, we can tell that, hey, yeah, just ADC got access. Someone just tried to send a packet over the Wi-Fi and see what exactly is running on these devices. So here's an overview of ThermWare. We first use the thermal camera to capture a sequence of thermal images. Then we extract some image level features and train a machine learning model to detect what's anomaly and what's a good code. And then we could detect if a malware activity is running on these devices. So to check it, we did a quick feasibility experiment. Here you see a BeagleBone Black, which is an off-the-shelf microcontroller. And here I have labeled 1, 2, and 3, which are the power management ICs, the storage card, and the microprocessor. So if we do like a file read and write operation over time, you could see that the storage IC gets heated up, and as we power off, it gets cooled down immediately. So in this work, we asked 2 research questions. First is that can we actually detect micro operations like file read and write only from these heat signatures? And the second is that, all right, if we identify these operations, can we see the sequence of this operation and classify if it's a good code or a bad code? I mean, if it's an anomaly or a malware. So let's look at the first question first, which is our image processing-based technique. So let's say we have this thermal image taken from a handheld thermal camera of this BeagleBone Black. Here I have marked the eMMC, which is the storage IC, the memory unit. And just by looking at the average pixel intensity of this memory block, we could see that whenever a file write operation is taking place, we see a spike or a change in the average thermal value of this block. And by simply filtering and smoothing, we could now apply a threshold and say that, hey, there was a file being written at these timestamps. We found that top 3,000 pixel gave us the best representation of region of interest, and hence we use a machine learning model to generalize this approach even better. So here we are using isolation forest and local outlier factors to classify if it's an anomaly or not. Our features include the minimum and maximum variability of each of these top 3,000 pixels, and then we simply train an isolation forest with 50 trees and run a sliding window of 2 seconds to detect anomalies. Here you see on the left-hand side, we detect 8 out of 9 file operations, and only we miss one around 20th second. Yeah, so now let us take a look at our evaluation setup and attack scenarios. We are using the BeagleBone Black running Ubuntu 18.04 and 3 thermal cameras ranging all the way from $500 to $11,000 with different thermal sensitivity and frame rates. We target 2 application scenarios, the most common ones that we find around us. One is a smart speaker, and another is a basic sensor like a temperature or an air quality sensor. And we emulate these operations on our BeagleBone Black, which is like recording audio, storing it in a file, text-to-speech, uploading it on cloud, and so on. We picked top 4 malwares of the Linux operating system, which are like crypto mining, softwares, and network scanning, brute force, ransomware, and so on. So this is our performance on file write detection. We perform file sizes ranging from 25 to 1,000 kilobytes. We didn't go even further because we saw that it saturates, and naturally larger file sizes are easier to detect because they leave a larger thermal footprint on the IC. And we see that cameras with higher frame rate, which is the FLIR cameras, they perform better than the ones with lower frame rate. This is our evaluation on malware detection. So we only call it a successful detection if we are able to detect the malware activity within 1 minute of the attack. Otherwise, we call it a false positive. And we run all of these malware on 3 different applications, which are smart thermometer, air sensor, and voice assistant. And we run all the 4 malwares on each of them separately. So here we show the device status, which is either idle, logging, speech to text, play music, and so on, and all the malwares running in parallel. And if you notice in play music, we have this network scanning attack, which has a large number of false positive, false negative, and we found that it's mostly because playing music is actually a very heat generating task because of speakers and kind of saturates the thermal sensitivity, while other events which are more natural, they are still like sensitive to catch up in the thermal camera. So I'll stop here and leave you with a more future work. So what if we could just go beyond security and maybe look at reverse engineering the code? So if I could point my camera to a smart speaker and see if it's actually running the correct firmware version, I could actually get the code itself. So I can, using the help of AI and code completion, we can get each step and each assembly level operation that has been happening and see what's exactly running without actually physically accessing the system. And if we go beyond IoT, I'm also thinking about like data centers. If you already have fine-grained temperature sensors, you could optimize the level of performance these data centers achieve. And I'm not just talking about thermal throttling. What if you could see each part, each core separately, and see that how you can optimize your nest scheduling process to have a better output of it. And thank you very much. I'm very excited about this topic. And thank you for listening. I'm ready for questions.
Thank you very much for the talk, Miles from UC Irvine. I think this approach is actually sounds really similar to the time gate-based approach for detection. So how do you compare your approach with the time gate one?
Yeah, that's a great question. I think instead of fighting with them, we would complement them very well. So for time gate, I guess you're talking about getting the scheduling time and see which process is running when. Is it true?
So it's sort of like if you want to run some malicious code, actual malicious code, it's going to cost some time, which you can detect the time difference.
Right. I guess, but for that, you'll need the software access to the system, right, as a detector.
You don't. So basically, for typical embedded devices, like you know almost exactly how much time is it going to take for accomplish a certain task. And if there is a certain malicious code going to be run, actual malicious code going to be run on that embedded devices, you can detect that by detecting the extra time costed for running a certain task.
Got it. I think it's easier to detect these time gate-based applications when it actually affects the computing. For example, if it's playing music in the background and if a malware is running in parallel, it might not affect the latency in actual music playing. So a person might not be able to tell if a malware is running in background. Or if these kind of malwares are very aperiodic, they could be like just happen once in an hour or so, then it's harder to detect with just time gate. But I would still say that we can complement any side channel like time gate or even power consumption. If you could see that the power consumption suddenly increased, you can complement with thermal or different side channels to make your features more stronger for this.
Mm-hmm.
Yeah.
Yeah, but how would you compare your approach with the
Yeah,
other
we haven't
approach?
compared it yet. So it would be interesting to see how it performs only based on time gate and only based on thermal. So yeah, that's there for future work.
Okay, thank you.
Thank you.
Hi, this is Yue Zhang from UC Merced. A very interesting talk. Yeah, I have two questions. First is like usually in the embedded platform, we might have multiple threads, multiple tasks that code running on the same time, right? So if the malicious software is combined with, for example, 10 good softwares, right? So how can you consider like for example, if there are 10 good software, right, and one malicious software, but the 10 good software also induce some heat on your image, right? So how can you separate them? Yeah.
Right, that's a great question and a challenge that we faced as well. What if the attacker tries to hide the activity in an ongoing process? If already a file write is taking place, someone can hide the file write within that and it won't be visible anymore. So it's definitely a challenge. What we need is more training data to see how well a system can perform on these kind of things. And in security, I think it's always a arms race between the attacker and defender, always trying to hide as much as possible. But I would say that if we are able to tap into more fine-grained information, which is the transistor-level thermal signatures and not just surface level, it would be much easier to detect these kind of attacks where someone is trying to hide it in an existing one.
Okay, the second question is more like if the malicious software just didn't write any file, but just leave some private data and send it to somewhere else instead of writing on the file. So how can your system can handle this?
Yeah, that's a great question. So right now we have just scratched the surface with file write, and the reason that we picked file write is because all of these top malwares actually have the fundamental block of file writing involved. But if there's just uploading to server, there would be corresponding thermal signatures towards the network card, right? There will be more packets transferred, so we could look at the Wi-Fi block, the network block, all of these, which again correspond to more data being sent, which might not be what application is currently doing.
Thank you.
Okay, thank you very much for your presentations. It has a very interesting idea. So yeah, I have a question regarding the way that you detect the heating, right, with the thermal camera. So you focus on the EMC. So yeah, is it possible to, because file usually interact with some kinds of NVM like the EMC. So do you try to your experiment on another hardware components? Because for the EMCs, it usually have a controller inside,
Right.
So it's very different compared with those kinds of the raw memory, like the NAND nor flash. So do you know? Because I'm not sure that the whole controller executed inside can cause more heating. So yeah, have you considered about execute your experiment on different kinds of hardware components to see if your algorithm and your stuff can detect it well?
Right. So there has been this trend of system on chips where people try to embed the memory blocks within one chip. So processor, memory, RAM, everything is in one IC. And it's a challenge to detect that if you don't have a good resolution camera. But so in these feasibility experiments we captured the video from almost a half a meter away. But if you have a good enough resolution camera and you could dive more closer, then even a system on chip will result in a different spatio-temporal feature on top of that IC. So if you could tap into that, then even though eMMC is not separately located, it will be in the system of chip at a different spatial location, which they often do because of better performance and more bandwidth. So then it could still do it, but it's a thing for future. So we want to tap into more fine-grained level of thermal signatures.
Thank you very much.
Hello, I'm Isaac Algren from University of Chicago, and I just have one question. You made a claim on one of the first slides about how microcontrollers typically don't have a lot of debug ports.
Yeah.
And this kind of work is based around the fact that you probably don't have debug ports on it,
Yeah.
which would be a lot easier way to see what's going on in there. And I just want to see how true that actually is. Everything that I know, everything that I've worked with has had a debug port on it. If you give examples about, I don't know, a real life application which debug ports aren't really used that much, that'd be much appreciated.
Right, that's a great question. I think that most of the development boards that we work on have debugging ports for our ease. But if we look at more consumer grade devices which are being deployed, for example, earbuds, right? So they'll have a always on microphone even if you put them in case. They don't have a USB port that we could plug it in. There could be a small drone flying here, insect kill drone, and they won't have a Ethernet port hanging out of it so that you can easily do. And I'm again talking about more consumer grade robots, not debugging and prototype ones. And that's more kind of our focus where you don't have that access to the physical layer and how could you non-invasively measure those side channels.
Thank you.
Great talk. I'm Akanksha from UMass Amherst. I wanted to understand a little bit more about the actual thermal cameras. So I know we just discussed about debuggable ports, but even with cameras, they would have to be located close enough to the device. How do you expect how is that very different from having a debuggable port? Because that's basically either you have another attachment to the device itself, which has a camera pointing to it, or something. And what's sort of the trade-off between the costs of these cameras and, you know, versus just having some type of debuggable port or something else on there?
That's a great question. The core idea for this work is a bit different from just using thermal cameras. We want to just extract the thermal signatures. So one way is to use thermal cameras, another way is to use fine-grained temperature sensors, which might just already, it could be like a sticker that you place on top of the board, or it comes with such kind of functionality. Or, and I'll take it at another level where I would say that not just capturing the thermal signature, but capturing a kind of a function that transfers from any operation to any output. So it's like a thermal impulse response, for lack of a better word, where you know that if a certain action takes place, a thermal signature is generated from a specific point, like an earthquake, and then it spreads out because heat dissipates at another region. And the way it spreads out in other regions, it might not be a network packet send, but just because the heat leaked to that area, you could capture that. And this kind of fine-grained level information, we not need a thermal camera for it. We can have more fine-grained sensors that are directly attached onto each of the ports and are not a part of the regular software. Otherwise, the attacker could also debug, like put malware in this, right? So that's the kind of area we are currently targeting to.
Okay, yeah, that's awesome. Thanks.
Thank you.